Okay. In this slide, we have another example. We not only define key reliability metrics, but we also visualize failure behavior using simple um, uh, test. And this is the example is destructive versus non-destructive testing, battery testing. The question is that smartphone company wants to evaluate the reliability of its batteries. Two testing approaches are considered: fully charged and discharged batteries repeatedly until failures. So measure the voltage, temperature, and the internal resistance without damaging the battery. Which method is destructive testing and which is non-destructive testing? And finally, the question is that what are the advantages and disadvantages of each method? So in this example, we want to compare destructive and non-destructive testing using a smartphone battery. In destructive testing, the battery is repeatedly charged and discharged until it fails. This method provides very accurate information about the actual lifetime and failure behavior of the battery. However, the main disadvantage is that the battery is permanently damaged and cannot be reused, making this approach costly when testing large number of the units. On the other hand, non-destructive testing involves monitoring key parameters such as voltage, temperature, and internal resistance without damaging the battery. This allows continuous observation of the battery's conditions over time and enables repeated measurements. However, since the battery is not pushed to failure, we cannot directly measure its exact lifetime. Instead, we rely on models and data analysis techniques to predict when failure is likely to occur. In practice, engineers often use a combination of both methods. And the destructive testing provides accurate lifetime data for model development, while non-destructive testing is used for condition monitoring and predictive maintenance in real-world application. Last week, I delivered some lectures regarding the destructive and non-destructive testing. So by using of this example, I want to just show you what is the difference between them. All right. In this example, this is another example. We compared um, actually destructive and non-destructive testing. So we have another example, field versus laboratory test or automatic systems. So an automotive company wants to evaluate the reliability of a new braking system. Two testing approaches are considered. First, testing the braking system under real driving conditions on roads. Second, the testing the system in a control laboratory using simulation equipment. Which method is field testing and which is laboratory testing? What are the advantages and limitations of each approach? So, as I told you in this example, we want to compare field testing and laboratory testing by using of an automotive braking system. In field testing, The system is evaluated under real driving conditions where factors such as weather, road, surface traffic, and driver behaviors all influence performance should be taken into account. So this approach provides highly realistic data and helps you understand how the system behaves in actual operating environments. However, it also introduces variability, making it difficult to control conditions and repeat tests consistently. So, in contrast, laboratory testing is performed in a controlled environment using simulation equipment, and you can precisely control variables such as speed, load, and temperature, which allows for repeatable and consistent experiments. So this makes it easier to isolate specific factors and analyze system performance. Let me add a new student. So, however, it also introduces variability, making it difficult to control conditions and repeat tests consistently. And we have another test, laboratory test. Uh, in contrast, laboratory test is performed in a controlled environment using simulation equipment, and you can precisely control variables such as speed, load, and temperature, which allows for repeatable and consistent experiments. So this makes it easier to isolate specific factors and analyze system performance, and uh, you can have that you can know that laboratory conditions may not capture all real-world complexities, and some failure mechanisms might not appear in the model. In practice, both methods complement each other, and laboratory testing is often used during early design and development stages, while field testing is essential for final validation and real-world performance assumption. Let me add a new student. Okay, this is another example about the accelerated life testing, ILT, of electronic component. The question is that an electronic component is expected to operate for 5 years under normal temperature, 25 degrees centigrade. To reduce testing time, engineers test the component at a higher temperature, 85 degrees centigrade, where failures occur within 2 months. Let me add a new student. Uh, the question is that how can engineers estimate the lifetime under normal conditions using accelerated life testing? What is the main idea behind these methods? So this is a question, and let me check the answer. Okay, in this example, accelerated life testing uh, is used to estimate the lifetime of an electronic component under normal operating conditions. Instead of waiting several years for failure to occur at room temperature, engineers increase the stress level by raising the temperature to 85 degrees centigrade. Did you remember we already talked about the ILT? So um, we can add some stress to the systems and to see that failure will be happen or not. At this elevated temperature, the component fails much faster within about 2 months. By collecting failure data, under these accelerated conditions, engineers can also apply models such as the Arrhenius model to establish a relationship between the temperature and lifetime. The key idea behind accelerated life testing is that higher stress levels accelerate the same physical failure mechanisms that occur under normal conditions. Using this relationship, we can extrapolate the result back to normal operating conditions and estimate the real-time data, which in this case is around 5 years. This approach significantly reduce testing time and cost while still providing valuable reliability insights. So, however, it is important to ensure that the failure mechanisms under accelerated conditions remain the same as those in normal operations to maintain accuracy. Okay, this slide presents a simple but very important example of stress factors using a power cable. In real engineering systems, different types of stress can significantly affect reliability. For instance, the high temperature accelerates insulation aging and may lead to melting in electrical cables. So, similarly, excessive voltage can cause dielectric breakdown in electrical cable, which is common failure mechanism in the electrical systems. In addition, overloading increases current flow, leading to overheating and eventual failure. This example clearly shows how environmental and operational stress directly influence system reliability. Yeah, I just want to add this one to show the stress factors. This is another example. In this example, I highlight the importance of sampling in reliability testing. So testing all 1,000 products is often impractical due to time and cost constraints. So we should select a representative sample of 100 units, for example. Different sampling methods can be used, such as random sampling, where every unit has an equal chance of selections, or stratified sampling, where samples are selected from different categories to ensure proper representations. However, if the sample is not chosen correctly, the result may be biased and misleading, leading to incorrect conclusions about system reliability. This is why proper test planning is crucial. So proper test planning was also one of the topic that have has been covered last week. So I just added this example to show how it works. This slide explains the concept of sensor data, which is very common in reliability analysis, as I told you. In this example, out of 10 tested units, 6 have failed by the end of the test, but 4 units are still operating. These remaining units are considered right sensor because their exact failure times are unknown. And in real world testing, it is often not feasible to wait until all units fails. So sensor data must be properly included in the analysis. Ignoring such data can lead to inaccurate reliability estimation. Here, I want to introduce the exponential distribution testing using the example of computer service. In many electronic systems, failures occur randomly and are not depend dependent on operating time. This means the failure rate remains constant over time. Such behavior is well modeled by the exponential distribution, which has the important property of being memoryless. So this makes it particularly useful for modeling random failures in systems such as servers, communication equipment, and electronic devices, and a lot of other examples we have to cover this distribution function. Okay, this example also explains the Weibull distribution, which is one of the most important models in reliability engineering. It is highly flexible and can represent different failure behaviors. When the shape parameter beta is less than 1, it indicates early failure, and often due to a manufacturer defect. When beta equal 1, failures occur randomly and similar to the exponential case. When beta is greater than 1, it represents wear out failures caused by aging and fatigue. So this behavior is commonly illustrated by the Base-Tube curve, which is widely used in engineering application. And we already saw this curve in one of the slides previously. All right. This slide introduced the Kaplan-Meier estimator, a non-parametric method used when dealing with incomplete or sensor data. And in many practical cases, such as medical studies or reliability testing, some units do not fail during the observation period. The Kaplan-Meier method estimates the survival probability step by step at each failure event, and one of its main advantages, as I told you in the previous slide, is that it does not assume any specific distribution, making it highly flexible and widely applicable in both engineering and biomedical fields. So the biomedical engineer in the class maybe will use this method later on in their projects, you know. Okay, this industrial example demonstrates the practical importance of reliability analysis in energy system, specifically wind turbines. By collecting data such as failure times, temperature, and wind speed, you can develop predictive models to estimate when failures are likely to occur, you know. And this enables condition-based maintenance, reduce unexpected downtime, and lowers maintenance costs. You know, we already discussed about all of these benefits. So ultimately, applying reliability analysis in such systems improve the overall performance and increase system availability, which is critical in modern renewable energy systems in power systems. Okay, this is a one example regarding the Arrhenius model, temperature acceleration. A company wants to estimate the lifetime of an electronic capacitor under normal operating temperature, 40 degrees centigrade, and instead of waiting for years, the capacitor is tested at a higher temperature, 80 degrees and 100 degrees centigrade. test results show that failures occur much faster at higher temperatures. So how can we use these high temperature results to predict lifetime at a normal temperature? This is a question. So by using of Arrhenius model. So in this example, we want to use the Arrhenius model to analyze temperature accelerated failures in an electronic capacitor. So instead of performing long-term tests at normal operating temperature, we increase the temperature to accelerate the aging process. So this is based on the physical principle that chemical reactions such as insulation degradation occur faster at higher temperatures. So the Arrhenius model provides a mathematical relationship between the temperature and failure rate, allowing us to extrapolate results from accelerated conditions back to normal conditions. This approach significantly reduces testing time while maintaining realistic failures mechanisms. So, okay, this is another example regarding the Eyring model, multiple stress factors. So the example is that a printed circuit board PCB is used in an outdoor environment. It is exposed to high temperature, 70 degrees centigrade, high humidity, 85% electrical voltage stress. Engineer perform accelerated test using combination of this stress. So the question is that why is a single stress model not sufficient, and how we can predict the lifetime under normal condition. Okay, as I told you, this example highlight the importance of Eyring model when multiple stress factors are involved. In real-world systems, failures are rarely caused by a single factor. For example, in a PCB, temperature accelerates chemical aging, humidity leads to corrosion, and voltage introduces electrical stress. So all of these factors interact with each other, making the failure mechanisms more complex. So the Eyring model extends the Arrhenius concept by incorporating multiple stress variables into a unified model. So this allows you to more accurately predict system reliability under realistic operating conditions, especially in harsh environments such as outdoor or industrial applications. This is an example related to inverse power law model, stress and lifetime versus lifetime. A mechanism bearing is tested under different load conditions. 50N lasts 5,000 hours, 100N lasts 2,000 hours, 150N lasts 800 hours. Question is that what is the relationship between load and lifetime, and how can we predict lifetime at a normal load? Okay, in this example, we want to analyze the effect of mechanical load on the lifetime of bearing. As the applied load increase, the internal stress within the material also will be increase and accelerating fatigue and wear mechanisms. The observed data clearly shows that lifetime decreases rapidly with increasing load. The inverse power law model captures this relationship mathematically, where lifetime is inversely proportional to stress rise to a certain power. This model is widely used in fatigue analysis and mechanical reliability studies. It allows you to predict system behavior under normal operating loads based on accelerated testing at higher stress levels. Okay, this is a example related to importance of data quality. So a reliability engineer collects failure data from 50 devices. However, some failure times are recorded incorrectly. Some data is missing. So question is that how does poor data quality affect reliability analysis? So um, these examples also highlight the critical importance of data quality in reliability analysis. So if failure times are recorded incorrectly or some data is missing, the resulting analysis may lead to incorrect conclusions. So for example, a wrong estimation of failure rate or lifetime can affect design decision and maintenance planning. High quality data must be accurate, complete, and consistent to ensure reliable modeling and decision makings. This is an example related to type of data and reliability. A test on electronic devices produces the following data: exact failure times for some units removed before failure, some data grouped into intervals. Question is that what types of data are present in this test? So in real world reliability testing, different types of the data are often collected simultaneously, and some units may fail during the test, providing exact failure times, while others may be removed or may not fail within the test duration, resulting in sensor data. So in some cases, data is grouped into intervals for simplicity, and understanding these data types is essential because each requires different analysis methods. This is an example related to complete data. A test is conducted on 20 light bulbs. All bulbs are tested until failure, and their exact failures times are recorded. The question is that what type of data is this? So again, this is an example of complete data where every unit in the test has failed and exact failure times are a variable known. So this type of data is ideal for reliability analysis because it provides full information without uncertainty. However, in practice, it is often expensive and time consuming to obtain complete data, especially for highly reliable systems. So this example is related to sensor data overview. A reliability test is stopped after 1000 hours. Some units have not failed yet. Question is that what type of data issue does this represent? Okay, sensor data occurs when the exact failure time of some unit is unknown. This typically happens when tests are stopped before all units fail or when units are removed from the test. So sensor data is very common in reliability engineering and must be properly handled to avoid biased results. Okay, this is an example related to write sensor data. We have 10 devices are tested for 1000 hours. At the end, 7 devices failed, 3 devices are still working. What type of data are these 3 devices? So write sensor data is as I told you, the most common type of sensor data. It occurs when a unit has not failed by the end of the observation period. In this example, the remaining devices are still functioning, so their exact failure times are unknown. These data points must still be included in the analysis as they provide valuable information about system reliability. So, this is a very simple answer. Okay, this is an example related to left sensor data. A system is inspected at the start of the test, and some units are already failed. Their exact failure times are unknown. So question is that what type of data is this? Left sensor data occurs when a failure has already happened before the observation begins, and in such cases, we know that the failure occurred, but we do not know exactly when. So this type of data is less common, but still important in certain applications, such as maintenance inspections or historical data analysis. This is an example related to left sensor data. Okay, example related to interval sensor data. A system is inspected every 100 hours. A component is found failed between 200 and 300 hours. Question is that what type of data is this? So interval sensor data occurs when the exact failure time is not known, but it is known to lie within a specific time interval. This usually happens when systems are inspected periodically rather than um, continuously monitored, And this type of data provides partial information and requires special statistical methods for analysis. Okay, this is an example related to data recording method. A reliability test uses manual logs by technicians, sensors to record temperature and failure, a central database system, and question is that what are the data recording methods used? Okay, this example shows different data recording methods used in reliability testing. Manual recording involves human input, which may introduce errors. Automated systems use sensor and data acquisition tools for real-time monitoring, improving accuracy. Digital database store and manage large volumes of data efficiently. And choosing the right recording method is very essential for ensuring data quality and also considering the reliability in the system. Okay, this is another example related to common data issues. During data analysis, the engineer observed missing values, extremely large outliers, and inconsistent formats. Question is that what are these problem calls? So this example highlights common data issues encountered in reliability analysis, and missing data can reduce accuracy. Outliers may distort statistical results, and inconsistent format can complicate analysis. And identifying and addressing these issues is a critical step before performing any reliability modeling. So this is my lecture today. Is there any